Hello friends, in this lecture we will continue to look at sampling process. We have been looking at the ideal sampling process, also called instantaneous or impulse train sampling. In this lecture we will look at the spectrum of the sampled signal obtained through ideal sampling. We know that in a digital communication system we need to first convert an analog signal into a digital signal. This conversion from analog to digital is obtained by the process of sampling followed by quantization. A sampler essentially converts the continuous time signal into a discrete time signal, and this process is known as sampling. We have seen so far that when a continuous time signal, say m of t, is multiplied with an ideal impulse train, periodic impulse train with period ts, so mt multiplied by the periodic impulse train, which we denote by delta ts of t. So mt into delta ts of t results in the sampled version of the signal, which is again an impulse train, but now the strength of each impulse is equal to the value of the message signal at that instant where the impulse occurs. For example, at t equal to 0, the strength of the impulse is m of 0. At t equal to ts, the strength of the impulse is m of ts, and so on. Mathematically, we represent this operation as the sampled signal m delta t equal to mt into the impulse train delta ts of t, which ultimately takes the form of the summation, which is pictorially represented here. Now, at this point, we had asked a question: are we not losing information because of sampling, because of discretization in time? To find out the answer to this question, we need to look at the spectrum of the sampled signal. And let us now understand how to obtain the spectrum or the Fourier transform of sampled signal. So we have with us m delta t, the sampled signal, which is equal to the message signal times the impulse train, which we write as delta ts of t. Now, if you want to take the Fourier transform of it, if we take the Fourier transform, then m delta t can be written in the Fourier domain, frequency domain, as capital M delta f equal to capital M of f. And using the multiplication property of Fourier transform, we know that the multiplication in time domain becomes convolution in frequency domain. So convolution, the Fourier transform of the impulse train, which we denote as Fourier transform of f of delta ts of t. Now, in the previous lecture, we have already obtained the Fourier transform of the impulse train, that is given as 1 by ts summation k from minus infinity to plus infinity delta f minus k fs. Now here we use the distributive property of the convolution. The convolution distributes over the sum, and we can write it as 1 by ts, because 1 by ts is a constant, we can write it in the front, summation k from minus infinity to plus infinity mf convolution delta f minus kfs. Now here we invoke an important property of the impulse function, that when a function is convolved with a shifted impulse, the result is a shifted function. Just to recall that if we have some function x of argument v, x of v, if this function is convolved with a shifted impulse delta v minus some v naught, then the result will be x of v minus v naught. The function convolved with a shifted impulse is the shifted function. Here x is capital M and v is f and v naught is kfs. Accordingly, we get here 1 by ts summation k from minus infinity to plus infinity m of f minus kfs. So m delta f is equal to, that is the spectrum or the Fourier transform of the sampled signal is given by m delta f equal to 1 by ts summation k from minus infinity to infinity capital M of f minus kfs. This is an important result. What does this result imply? This result says that the spectrum of the sampled signal is the original spectrum M of f replicated at the integer multiple of the sampling frequency fs. So the same spectrum M of f appears at fs, 2fs, 3fs, minus fs, minus 2fs, and so on for every integer multiple k. So the process of sampling results in infinite copies of the same spectrum M of f, each scaled by the factor 1 by ts, or which is f of s. So this can also be written as fs summation k from minus infinity to infinity m of f minus kfs. Pictorially, we can show it like this. Let us assume that m of t is a band limited signal. So let mt be a band limited signal, which is, say, band limited to w hertz. Say this is minus w and this is plus w. So the spectrum of m of f is non-zero only in the interval from minus w to plus w, and beyond it, it is 0. That is what we call a band limited signal. So when we sample the signal, the spectrum of the sampled signal is then the same spectrum m of f scaled by fs appearing at integer multiple of fs. So fs, 2fs, minus fs, minus 2fs, and so on. And these frequencies can be denoted as the boundary frequencies as w minus w. Here it will be fs minus w. This will be fs plus w, and so on. Similarly, here it will be minus fs plus w here, minus fs minus w here, and so on. So the same spectrum replicated at all integer multiple of the sampling frequency fs. What is interesting to note here is that the same spectrum is appearing around 0 also. That means it matches with the original spectrum of the signal. The only difference is that now the height of this spectrum, amplitude of this spectrum at f equal to 0 is fs, which was 1. So there has been a scaling here If we use a filter here, say a low pass filter whose cutoff frequency, say B, is such that it is greater than W and less than Fs minus W, in that case, we can recover this spectrum from this entire spectrum, and this spectrum is nothing but the original signal, and therefore we can recover the original signal. As far as scaling is concerned, we can take care of it by taking the gain of the low pass filter equal to Ts, so that Ts into Fs becomes 1 and we get exactly the original spectrum after low pass filtering. So this is a low pass filter. What is important here to note is that this recovery of the message is possible when this Fs minus W frequency is greater than this W frequency. So what are we saying? When Fs minus W is greater than W, in that case it is possible to have a low pass filter with cutoff frequency such that which is greater than W and less than Fs minus W to recover the message signal. Now, what does it mean? It means that the sampling frequency must be greater than 2W, and it is one of the most fundamental results in digital communication and digital signal processing. It says that a signal can be recovered perfectly from its samples if the sampling rate or sampling frequency is greater than twice the maximum frequency of the signal. Here the maximum frequency is W, so twice that of W is the frequency. The sampling frequency should be greater than. This important result is known as sampling theorem. We shall formally state this theorem and talk about related aspects in the next lecture. Thank you.